We next cover a phenomena called surface tension, which is quite prominent in fluids at rest. Fluids at rest who have an interface with other fluid, most often with the gas. You might have seen little insects which seem to be walking on water. Here's an insect known as a water strider, which is walking on the surface of water without sinking. How is that achieved? Similarly, in this picture, we have a cup of water on the surface of which a paper clip is floating. What is supporting the weight of this paper clip? Clearly, it is not buoyancy because the pen or the paper clip not submerged in water. So what's going on? The explanation of these two phenomena lies in what is called surface tension. At the interface between a liquid and a gas, the upper surface is under tension. A molecule which is not at the surface is being pulled on each side by molecules of the liquid all around it, but a molecule on the surface is pulled down. And because it is pulled down and it can't go down, there is a tension created on that surface. If we apply a force vertically on the surface, the surface bends, produces a small dip, so that the end of the surface, at the end of the dip, the surface is inclined. And the vertical component of this inclination balances the vertical force which is shown by a red arrow. This is what is happening to the clip. You can see the water around this clip is showing a depression. So it's like a membrane which is stretched and supports the weight of the clip. Similarly, you notice in details that each leg of the water strider, there's a cup-like formation of the water surface. The surface is curved and the tension on the surface is now providing an upward force to each leg. The surface tension in liquid can be measured by a small setup. We have a U-shaped frame on which we have a slider. If we create a film of liquid on this, that film of liquid can support a small force F. This small force F depends upon the length L of the film in the horizontal direction as shown. And this force F is equal to sigma L, where sigma is termed as the coefficient of surface tension for the liquid gas pair. It depends upon the liquid and the gas both. For water in contact with air, the value of sigma, the surface tension, is 7.56 into 10 raised to power minus 2 Newton per meter. It is a very small quantity, but can become significant in many cases, the two of which we have already discussed. The force of surface tension is also responsible for formation of bubbles when a droplet of water is in contact with the surface. In fact, here it is the three surface interface, the solid, air and liquid, that are in picture. As the adhesion increases to the right, the cohesion decreases to the right and the wetting increases. We say that at this location, the wetting is minimum, and at that location, the wetting is maximum. You would have seen that if I have waxed paper, a droplet of water onto that wax paper would almost look like this on the left. But on an ordinary paper, the droplet of water would spread out like this, because the water wets an ordinary paper, but it does not wet a waxed paper. On a waxed paper, the adhesion with the paper is low, cohesion within the water molecules is high. We introduce a term contact angle. Contact angle is the angle that the droplet makes with the surface. So here the contact angle is large, here the contact angle is small. These are surfaces, in wetted surfaces, the contact angle is low. On glass, water has a very low contact angle, almost zero. Water wets the glass almost completely. But if there was mercury, the mercury does not wet glass, and the mercury would be sitting on a glass with almost spherical bubbles, so that the contact angle alpha is 180 degrees. This wetting results in liquid meniscus as shown. On the left is a fluid like mercury, which does not wet the tube material, and so we have a convex meniscus. On the right is a liquid that wets the wall of the tube, so we have a concave meniscus. Water in a glass tube forms a concave meniscus. Mercury in a glass tube forms a convex meniscus. The meniscus of mercury in a glass would be much more pronounced than that, and it would be, the contact angle would be 180 degrees there. And the contact angle, if it is water, then the contact angle here would be 0 degree. So meniscus would be much sharper. We next calculate the excess pressure inside a bubble like a soap bubble. Let's form a soap bubble of radius r. The pressure inside is a little more than pressure outside. How do we relate the pressure difference to surface tension? Consider half the bubble below the equator. The free body diagram of this bubble shows the forces in this bubble. There are two kinds of forces. This set of forces are the forces that act on the surface of the bubble, and they are because of surface tension of the liquid surface and the air. This all around the circumference of the cut that we have created. And these forces are the pressure forces that act on the hemispherical surface because of the pressure, excess pressure inside. If the excess pressure is P, then we can show by simple calculations that this pressure force, the component in the vertical downward direction is P times pi r square, where pi r square is the area of the diametrical plane of this bubble. And the surface tension force upwards are sigma times the length of the equatorial cut, which is 2 pi r, where r is the radius of the bubble. But that is only on one side. A bubble would have two sides of the surface. One, the outside, in contact with the outside air, and one inside, in contact with the outside air. So total surface tension force would be sigma times 2 times 2 pi r. And so the equation would be the P internal gauge pressure, that's above the outside pressure, into pi r square, the area of the equatorial plane, is equal to 2 pi r sigma, which is the force on one side of the hoop, into 2, because there are two sides to the hoop. So the internal pressures is 4 sigma by r. It is interesting. This pressure or the excess pressure varies inversely like r. That means lower the radius, we need more pressure. So while blowing a bubble, we need a larger pressure to start the bubble, and then the pressure needs to decrease. We need more air in there to increase the diameter, increase the size of the bubble, but the pressure inside must be lower. There is an estimate of this internal pressures. We are talking for water with a sigma of 2.5 into 10 to the minus 2 Newton per meter, and the radius at 1 millimeter, that is 0.001 meter, and this gives you 100 Pascal. 100 Pascal is a very small excess pressure. In this video that we showed, when the two bubbles coalesce together and we stretch them by taking our hands apart, the bubble surface acquired this shape. This is because surface tension results in stored energy in the film, and the surface acquires a shape with the minimum energy, and that minimum energy occurs when the surface area is the minimum. So this surface is the minimum surface that is formed with the amount of air that we had in those two bubbles. Similarly, we showed that when the experimenter played with a bubble with gloved hands, wearing the woolen gloves, the bubble were very spherical and they were jumping from hand to hand. This is because the wool is not wetted by the soapy water that the bubbles are made of. In the context of surface tension, let's do an example where we calculate the maximum diameter of an aluminum ball that can float on water. There is a small aluminum ball which is floating in water. We have to find out the maximum diameter that this ball can have. If the diameter increases, the ball would sink. That is, the surface tension force would not be enough to keep the ball afloat. It should stand to reason if we argue that is at the maximum size of the ball, when the weight of the ball would be maximum, the surface tension force would be maximum. And the maximum surface tension force would occur when the ball is immersed up to its equator. That is, half the ball is inside and half the ball is outside in air. So that the length of the water-air interface at the location of the ball is maximum, equal to pi times the diameter of the ball. Now we draw a free body diagram of the ball. It has three forces. One is the weight of the ball, mg. Other is the buoyancy force on the ball. The buoyancy you studied in high school is related to the volume of the liquid displaced, or rather to the weight of the liquid displaced. Here, the volume of the liquid displaced is equal to half the volume of the sphere, 2 by 3 pi r cubed. And so the buoyancy force would be rho of water times g times 2 by 3 pi r cubed. The weight would be rho of aluminum times g times 4 by 3 pi r cube. And the third force is the surface tension force, which acts over a length pi d. So that the force is sigma pi d. If we put all the forces together, we get the weight should be equal to the buoyancy force upward plus the surface tension force upward. Unlike in the case of bubble, there is only one interface here. So the length we have taken is pi d. And plugging in the value for various quantities, we get d is equal to 6.4 into 10 to the minus 3 meters, or 6.4 millimeter. Not a very small diameter. So aluminum spheres of diameter 6.5 can float on water if they are carefully launched. Another consequence of surface tension is the capillary action. Here you see there was a droplet of water on a surface, on a table top, and if a paper towel is brought in contact with this, the water is soaked up by the paper towel. What pulls up this water? It is the force of surface tension. In this picture is shown a container where there is a blue fluid and a number of tubes with varying bore. The leftmost tube has the largest bore, and the bore size decreases as you move to the right. So this tube has the smallest bore. And you see the water, the liquid, the blue liquid rises up in this tube beyond the level contained in this tube. The liquid is not maintaining its level. The liquid is rising up and rising up more in tubes with a smaller bore. Tubes with their very small bores are called capillaries, and so the phenomena is termed as capillary rise or capillarity. Another example of capillarity is that water, the colored water from the higher or from the cup with a higher level of water is flowing into this over the edge through a rag. To analyze this capillary rise, consider a capillary in which the water or the liquid has risen up to a level H. Of course, we ignore the meniscus and measure only height in the main tube. We consider the free body of this fluid. This free body is shown here. Clearly, the pressure at this point is the same as pressure at this point. Same level in a liquid connected with the same fluid. And the pressure here is atmospheric. So pressure there is atmospheric. So in this, the pressure on the top is atmospheric, pressure on the bottom is atmospheric, and we have not shown it. Other forces, the weight of this column of liquid, which would be the density times the volume of the liquid, which is pi r square, the cross section, times the height h, times g. And this is balanced by the surface tension force, sigma into 2 pi r. Assuming that the contact angle is 0, so this force is vertically upward. Water in a glass tube would have sigma is equal to the contact angle to 0, so this force would be sigma into 2 pi r. Clearly, at equilibrium, the two forces must balance, and therefore we can get a capillary rise H is equal to twice sigma divided by pi r g. The larger the value of r, the less is the capillary rise. Let's estimate this capillary rise for water in a capillary of diameter 1 millimeter, that is of radius 0.5 millimeter. And if we plug in the value of H the capillary rise is 29 millimeter, almost 30 millimeter, almost 3 centimeters in a tube with a bore of 1 millimeter. An interesting phenomenon. All the trees and vegetation on earth need water for their growth. The water is sucked up through the roots through a system called xylem. And it goes up. The product of synthesis travel down through a system called phloem, shown here with yellow arrows flowing down. Now the tallest trees on earth, over 100-meter tall, the redwoods of California, USA, over 100 meters tall. We need a pressure differential of about 12 atmosphere or 1.2 megapascal to raise water to the topmost leaves. There are many ways by which this kind of pressure difference is created, not the least of which is the capillarity. The capillarity of the sapwood of redwood trees, which is in this region around the tree trunks. It's a foam-like wood, fibrous wood, with a mean diameter of xylem at about 50 micrometers. Of course, the phloem are just behind the bark of the tree, just inside the bark of the tree. And they produce a flow downwards. In fact, it is argued that this flow of fluid of the product of photosynthesis downwards also help in raising the water up, because it creates a kind of vacuum up there when the water flows down. But you remember that even the absolute vacuum produces only about 10 meters of water rise in a barometric tube. So this is only a very small portion. It is a complicated phenomena and we cannot explain it fully here, just to give an indication of that the capillarity is part of the answer. That brings us to the end of this lecture. In the next lecture, we will do forces on submerged surfaces. Thank you.